Continuing on now, this calculation down here, I might just I think I explained it in the previous lecture. Say for example, we have the example of the mass of the bags of cement, and suppose it's set up that the average is 40.1 kg, but there's a bit of variation, something like this. And suppose the question was, what's the probability that the mass is greater than 40 kgs? So the way this thing is set up is that the probability that the mass is greater than 40 is the area here. Now this goes on forever and ever, and we're going to use the language of it's a long because it's bigger than half, right because it goes to the right, tail. Okay, and this will be the probability that the mass of a randomly selected bag of cement is greater than 40. Now I can do greater than or equal to, as we discussed in the previous lecture, it makes no difference. So this probability, so what you have is two bits of information about the bags of cement: the mean average, which is where the peak is, and the standard deviation, which basically says how spread out the peak is. And from that you can calculate the probability it's equal to this area. Now how would you calculate an area? Okay, so we'll worry about that in a second, but what this is kind of saying is that what you can do is you can transform this from an M picture, which would be an X picture in this notation, to a Z picture. So the Z picture is a normal distribution where the average is 0, so the peak is at 0 and the standard deviation is 1. So you'll put this 40 into this formula here and you'll get out, we'll call it Z1, and then you've got this area here, and it turns out that this area is equal to this area is equal to this, which would be the same as the probability that Z is greater than Z1, greater than or equal to. You might remember this from Leaving Cert or not. Okay, so just this calculation, just a little proof is done on the next page. If you're interested in why it's true, it's here. Well, it's just some stuff from calculus. So the question is, how do you calculate these areas? Like, how do you calculate that area? Well, if you remember your integration, if you want to calculate areas under curves, as I said, you need integration. So this should be, say, the integral from Z1 up to infinity. Now we won't talk about how you calculate infinite integrals because we'll see infinite integrals again in the next semester if you choose it. The density function, which is this f of z here, dz. So you have to calculate this integral. And how do you calculate an integral? You anti-differentiate. Now, you might remember from the previous chapter, you can't anti-differentiate e to the minus z squared. So we've got a big issue. And similarly to the end of the previous chapter, when you've got a problem that you can't solve exactly, you have to use approximation. Okay? Now, we're not going to approximate these every time because there's just too many calculations. So what we're going to do instead is we're going to use a table of values. Okay, so these numbers, so this, I'm going to have to email you this table, which you might have seen before. So these numbers are approximations, and things similar to the Euler method can be used to find them, but we won't worry, you'll just take it as read. So there's a few, okay, so we got to be very clear about this picture. So the first thing is that all these numbers here, these numbers here are these areas. So see there it says table entry. These are the table entries. And this is an area. Now I'm going to change this to Z1 because I just don't like the way it is. So this area, and it would be equal to the probability that Z, which is on the x-axis here, is less than or equal to Z1. So these numbers in here are all areas, and they're all probabilities, and as you can see, they're numbers between 0 and 1. So all these things are areas slash probabilities. Let's write probs. Okay. Now what you have then is these numbers on the side are the Z1. So suppose for argument's sake Z1 was equal to say 1.23. Say that was the value of Z1, and like, so these Z values, where are they going to come from? Well, you're going to put values, now this is M here, but think of it as X. You put like 40 into this formula and you get out a Z value, and these are the numbers you're looking at. So suppose this might be, what's the probability that the mass of the cement is maybe less than 40.2 for argument's sake. You turn into a question like this, and you're trying to get the area in the long left tail to be the probability that Z is less than, say for argument's sake, 1.23. So what you do is you go down to 1.2 here, and you go across the 0.03, so you get the first decimal place here and the second decimal place here. And this number here, you see it lines up. If this was Z1 1.23, the long left tail would be 0.8907. So I might write down something like the long left tail, LLT, long left tail, it's long because it's bigger than 50%, left because it's going left, tail because it's a tail, of 1.23 is equal to 0.8907. Now if you want to think about what Z is, I think we mentioned this in the previous lecture. Z is a number of standard deviations. So, or just Z1 even, or Z even, yeah. So Z is number of standard deviations. And if you're confusing, so basically here standard deviation is 1. So 1.23 is 1.23 by 1. So it's 1.23 standard deviations. But that will correspond back here. Say if you put in 40 and you got minus 1.23 for argument's sake, then 40 would be 40.1 minus 1.23 times the standard deviation, whatever that is. So Z is a number of standard deviations. And sometimes the number of standard deviations looks like a probability. So for example, what about the probability that Z is less than or equal to 0.5? Now Z is a number of standard deviations. We'll just do 7 for argument's sake. So we go 0.57, and we get, here it is, 0.7157. Okay. There's a few things that we must remark as well here. We must say that what's the total area? Well, the total area is the total probability. And if areas are probabilities, it must be 1, as in 100%. And it's symmetric. So like if you look at what's less than, so remember this is the Z, it has its peak at 0. So what proportion is less than 0? Well, it's going to be 0.5, 50%, because it's 50% here, 50% here. And it's symmetric. Now what the symmetric means, and we'll probably see it in questions, but say for argument's sake, the short right tail of 1.23. So this is short right tail of plus 1.23. So that would be this area here. Now, how would you find that little area there? Well, you'd have to do 1 minus this. Are we talking 0.1093? So if you know the long left tail, you can find the short right tail by doing 1 minus that, because they have to add up to 1. And we've got a symmetry as well. So the short right tail of 1.23, that's this area here. I could write it's 1 minus the long left tail, that's fine. We'll write stuff like that in the thing. But this is equal to, say, the probability that Z is greater than, and it doesn't matter if I include equals to 1.23, is actually the same as the probability that Z is less than minus 1.23. So if you go over from plus 1.23 to minus 1.23, if you were to do that, say there, the area in this short left tail is this, if it's at minus 1.23, is the same as the area in the short right tail. So this is the same as the short left tail of minus 1.23. Okay, now we'll use this table again and again, but maybe in the scanned notes I'll leave this particular table so you can see all of the notes. We'll mostly learn about this by way of example though. Okay, ignore them. Right, so first question. So however you kind of do this, I'm not too worried. So there's different ways. Like you can use all this notation. You can just use tails. You can use pictures. I'm probably going to use some kind of combination of all three. And as long as what you're writing down is communicated properly, I don't mind exactly how you get the answer if you get the answer right. Usually that's my kind of what my thinking is in this chapter. Okay, so what z value has a 20% probability of being exceeded? So I think the pictures for me is the best way to go. So let's draw our z. Its peak is at 0. And we're looking for a z value. So this is z here. So what's on the y-axis here is what's called the probability density. And we're looking for a value of z such that the probability that it's exceeded, so that you get something bigger than it, and I'm going to call it z1, is 20%. Okay, and this tail goes on forever. So this area is 20%. Okay, now you have to work with what you've got. And what we've got is long left tails. Now, I'm going to send this table, and there's another one as well. If you want to find your own table on the internet that does, for example, short right tails, I don't mind. You're allowed to use resources like that to do your assignment. There's no issue. So it is possible to find tables that do short right tails. Okay, but I'm just going to use this one. Okay, so okay, we've got 20% here, so we want to find the z value. So this one is a funny way around. We have, well, maybe let's just turn this into a slightly different problem. If there's 20% in that short right tail, because it adds up to 100%, there has to be 80% in the long left tail. So we're trying to find the z value with 80% in the long left tail. That's what we're looking at. So I'm going to look at the table here, and what we're looking for in here is a z value such that this area is 80%. So you have to remember these areas are 80%. So we're going to find an area of 80%. Let's find 80% in here. Now you mightn't be able to find exactly 80%, but you just have to go to the closest possible one. If there's a tie, I'm not going to be too worried, but because a lot of, so we're going to be assuming things later on are normally distributed and they aren't. So you can't be very, very precise anyway. So if there's a tie and you pick one over the other, there's not a big reason, but maybe we'll see one where there's maybe a possible reason that you pick one over the other. So you need to find the closest you can to 0.8. Now 0.8023 is 0.0023 away, but this one is only 0.005 away. So this I'm going to use, and I go back. That's the second digit. That's the first digit. So the z value that has a long left tail of as close as we can to 80% is 0.84. Okay. So we know that z1 is equal to 0.84. Now we could, maybe if we did an argument there, like maybe, what am I thinking of? Yeah, so yeah, that's grand, because if you're being really, really fussy, and there's no point going down to this fourth significant figure is what I'm getting at, but there's 0.7995, so the probability that you're bigger than this is 0.8005, which is definitely, or sorry, 0.2005, which is definitely bigger than 20%. Like maybe if this one was closer, like say if you 0.8001, then you could be really fussy and say, oh, there's only a 19.99% chance of it being exceeded, but there's no point being that restrictive anyway. Anyway, however way you look at it, you get 0.84. So that's this kind of reverse problem where you have the probability and you want to find the z value. Usually it'd be the other way around. You have a z value, You want to find the probability. Okay, so I don't really have any idea what's going on here. There's no other way that I can think of doing it. Okay, let's look at another problem here. Due to natural variance, so that's just normal things being different, etc. When a river engineer measures the ammonia level in a river sample, the results are not uniform. So the idea here is this river engineer looking at the ammonia. Now, I don't know why that's... I thought this is something to do with environmental engineering, but anyway. So they're looking at different places in the river. Not all the water is exactly the same. So when they measure the ammonia level, it's not uniform. Historic records, so previous measurements, suggest that when tested, the ammonia level in one river is normally distributed with an average of 0.2 milligrams per litre and a standard deviation of 0.04. So this is the average, and this is a measure of how spread out it is. Okay, assuming that the statistics have not changed. Now what that means is, when I say the statistics have not changed, the amount of ammonia, the average is this, standard deviation is this, and it's still normally distributed. So normally distributed with a mean of this and standard deviation of this is what it means by the statistics have not changed. I'm going to write something next page. Yeah. Calculate the probability that a randomly selected sample from this river has an ammonia level less than this or between these two numbers. Okay, so what I'm happy as long as what you write down is consistent and well communicated. The notation doesn't have to be exactly as I go for, but this is what I would recommend. I would name the random variable, which is the amount of ammonia in a randomly selected sample. The next one is such. I'm going to call it X, and I'm going to write down that it has a normal distribution with this average mean and this standard deviation. So how I do that is as follows. Let X be the ammonia level in the sample, and X is, this symbol here means distributed as. So it describes what type of random variable it is. It's a normal random variable with an average of 0.2 and a standard deviation of 0.004. Okay, so what are we looking at here? So let's draw some pictures. So we're looking for the probability that X is less than 0.014. So let's draw the bell curve for that. So I said, if you give me the right answer and it's communicated well, I don't mind. I recommend personally drawing something like this. So the average is 0.2. So this is X, and we don't really need the y-axis, to be honest with you. Yeah, we really don't. We could put it over there if we wanted, but we don't. We're looking for the probability that it's less than 0.014. And remember, probabilities are areas, so we're looking for the area here. Okay, so what we need to do is we need to transform this question from a question and a picture about X to a question about Z. Now, why do we do that? Well, the reason is, if you want to find this, strictly speaking, you have to integrate this really, really complicated thing where the mu here is 0.2, the sigma is 0.0, whatever it was, 0.04, and we can't integrate this thing. So we translate it into a problem about Z. Now, you still can't calculate that, but we have a handy table. So basically, you relate every single question about a normal distribution back to this Z, which is normally distributed with an average of 0 and a standard deviation of 1. And the probabilities surrounding Z are on this table. Okay, so we're going to translate this question, and how we get the corresponding Z value is we use this thing. We could call this a Z transform. Now, it's actually not called that, but we'll do it anyway. So the corresponding Z value is, we'll just write out the formula here, X minus mu over sigma. So the X value that we're transforming is 0.14. The mu is the average, 0.2, divided by, that looks like a 6 there, it's not drawn well, it's a sigma, is standard deviation 0.04. And apparently this is equal to minus 1.5. So this area that we're looking for is equal to a different area. This time I will do the the axis because I want to put it at the peak. The average here is 0, this is Z, and so the 0.14 goes to minus 1.5. And the question essentially is find this area here. Now we might just see how here again the Z is the number of standard deviations. Because if we look at the standard, so the difference between these is 0.06, and that is 1.5 by standard deviation. So that's why Z you can think of as the number of standard deviations. Okay, so what we want is this, we're looking for the short left tail of minus 1.5. So what we're going to do is we're going to do a bit of messing around. We're going to say that this is equal to the short right tail of plus 1.5, which I think I will draw down here. So I'm saying this probability, the answer, I'm going to write answer, I rarely write answer, but I'll write it here. So the answer is equal to, so the area in the short left tail, but symmetry is the same in the area in the short right tail. So instead of minus 1.5 plus 1.5, this is still the Z, and this is still the area. Now, of course, if you want to go off and find a table which gives you the short left tails, off you go. So we don't have, unfortunately, the short right tails. We have the long left tails. Sorry, we don't have short right tails. The long left tails. So what we should do is say that this area here is the total area, the whole thing, which is just 1, minus the area in the long left tail. So some people will be perfectly capable of making this argument without drawing the pictures. I think the pictures explain, and if you want to, it's kind of up to you whether you include them or not, really. And this is a number that we can get off the table. So what we're saying, let's look at everything. So we've got an X problem that we translate using this formula to a Z problem. Using symmetry, we convert the area in the long or short left tail to the area in the short right tail. And we say that if we look at the whole area and chop off the long left tail of 1.5, then that gives us this little bit that we're looking for. And the reason we do that is because we can only really work with long left tails. So the long left tail of 1.5, we go here. So if you go down to 1.5, and of course, what's the second? Well, it's 1.50. We get this 0.9332. Okay, and so we get the answer here is this, which is, you know, if you wanted, it's 6.68%. Well, that number there is equal. Now, we usually won't worry so much about approximations. We're going to talk about rounding a lot in the last chapter, but in this, everything is rough. Like the assumption that the statistics haven't changed, that it's even normally distributed in the first place, are all dodgy. So there's not much point, like really maybe some of these percentages, really we can only go to one significant figure. Okay, the second part of this question is, so it is, what is the probability that it's between 0.14 and 0.26? And the easiest thing here is to note that there's a symmetry here. So that, let me just draw it. So 0.2, if you go back to 0.14, that distance is 0.06, it's 1.5 standard deviations. And if you go up to 2.6 or 0.26 as per the question, that's also 0.06, well, 0.06 is 1.5 standard deviations, so it's going to be 1.5. So what I'm saying here is, if you put Z equal to the X value here of 0.26 minus the mu here is 0.2 over the standard deviation 0.04, you're getting plus 1.5. So this number here is minus 1.5 standard deviations. This is plus 1.5 standard deviations. So we know that this probability, the area between these two, is equal to the area between minus 1.5 and plus 1.5. And now I'm a little short on the time, so I'll do it the obvious way, and then we'll look at a possible shortcut. So I'm not drawing the x picture here, I'm just drawing the z picture, because I know from symmetry we're just looking at between minus 1.5 and plus 1.5. So like if you transform both of those, that transforms to that transforms to that. So the probability that you're between those two is the area between those two. And the way you do this is you do the long left, now I'm going to use this language, so long left tail of 1.5, so all of that, take away the short left tail of minus 1.5. So if you don't understand that, maybe draw yourself a little picture. So if you do from here the whole way down, so find that area, take away that area. Now we've already found the area in the short left tail, because it was the answer to the previous part. Yeah? So, and we've already found the long left tail of 1.5 from the tables, it's 0.9332. Take away this, we've already found this little tail here to be 0.0668. And we'll just go to the calculator with that. And we get an answer 0.866. And if we're being rough, approximately 87%. So what this actually, this isn't something really special about this